So hi everyone, welcome back to the Oxford Discrete Maths and Probability Seminar. So it's a great pleasure to have this afternoon Jinyoung Park from Stanford, who's going to talk about thresholds. Thanks.
Thank you very much for this invitation. It's my great pleasure to give a talk at this seminar. So today I'm going to talk about thresholds, and so our new result is this. So this is so-called the Kahn and Kalai conjecture, and in the first part of my talk, I'll explain. I plan to explain the meaning and the motivation of this conjecture, and then in the later part, if we have time, then I will say a little bit about our proof ideas. That's our plan. Oh, by the way, so if you have any questions, then please feel free to stop me anytime. I love to be stopped during my talk. So let me start with some basic definitions. So here in my talk, we use X for a finite set. So X is just any finite set, and 2 to the X for the power set. And we use mu p for the p-biased product probability measure on 2 to the x. So that means for any subset A, mu p of A is defined to be p to the size of A times 1 minus p to the size of the complement of A. And we use xp for the random variable whose distribution is mu p. So simply speaking, xp is just the p random subset of x, which means we choose each element of x with probability p independently. So here are some examples. If we take X to be n choose 2, which is the collection of all of the edges in the complete graph on n vertices, then XP is simply GMP, the Erdos-Urani random graph. So we have n vertices and we choose each potential edge with probability P independently. On the other hand, if our finite set X is the collection of all of the k clauses from n variables, in this case, xp can be viewed as a random CNF formula. So our background, so motivation of the Kahn and Kalai conjecture comes from the random graph theory, but actually I want to say that our result applies to any finite setting. And then we use calligraphic F for an increasing property. And again, simply speaking, this just means adding an element does not destroy this property. So here, some examples are for okay, do you hear me? Because I was just muted. Okay, so in the first example, if we look at the random graph setting, then the property to be connected or the property to contain a triangle, those are the examples for an increasing property because adding an edge does not destroy this property. And also, if we are in the second example, in that case, the property to be not satisfiable is also, again, an example of an increasing property. So in the picture on the right-hand side, I draw this circle. This is 2 to the x with a natural process structure. So we have the empty set at the bottom and the entire set on the top. Then an increasing property looks like this. So this means whenever we have an element in this increasing property, then everything that contains this element is also contained in the increasing property F. Okay. So do we have any questions about those basic definitions? Okay, so now let me define the thresholds. A well-known fact is that for any increasing property F, so we assume that F is not the empty property or the entire property. In this case, mu p of F, which is by definition equal to the probability that XP satisfies the given increasing property F, this is continuous and strictly increasing in P. So in the picture below, so mu p of F looks like this. So for example, if P is 0, then so if we think about the example of containing of what can I say, being connected. In that case, if P is 0 in the random graph setting, if P is 0, then no edges are present. So with probability, the probability that GMP is connected is 0. So we are here. On the other hand, if P is 1, in that case, all of the edges are present. So the probability that GMP is connected is 1. And a well-known fact is that as we increase p from 0 to 1, the probability that xp satisfies the given increasing property also increases from 0 to 1. So we have this graph. And so because this function is continuous and strictly increasing in p, so there must exist something called pc of f, for which this measure up of f is exactly 1/2. And this pc of f is called the threshold for f. So from the definition, up of f, so roughly speaking, this means if we are below this threshold, then it's unlikely that our xp satisfies the given increasing property f. On the other hand, if p is larger than the threshold, then it's much more likely that our random variable xp satisfies the given increasing property f. So this is the rough concept of the threshold. And if you are familiar with the random graph theory, then you have seen this Erdős-Rényi threshold. So in the Erdős and Rényi defined a threshold function for the given increasing property fn in this way. So this definition seems a little bit different from our definition of the threshold, but by the well-known theorem by Bolobosch and Thomason, we know that our definition of the threshold is always an Erdős-Rényi threshold. So basically, we will just mixedly use the notion of our threshold with the notion of the Erdős-Rényi threshold. Okay, so are there any questions so far? Okay. So in this part, I'm going to explain the Kahn and Kalai conjecture. And this is a very strong conjecture. And Kahn and Kalai, in their paper, they said it would probably be more sensible to conjecture that it is not true. But yeah, so this is our new result. And the fundamental question behind this conjecture is this: what drives the threshold? So to answer this, so the Kahn and Kalai conjecture try to answer this question. And so in this part, what we are going to do is to examine some of the examples to build up some observations to answer this question. So in the first example, our x is n choose 2, so our xp is the Erdős-Rényi random graph GMP. And in this example, our increasing property is to contain a copy of h, where h is this little graph. And our first question is, what's the threshold for GMP to contain a copy of h? So yeah, because we are interested in the number of copies of h in GMP. So this is again a random variable because GMP is a random variable. So our usual suspect is to, so when we study a random variable, the usual starting point is to examine its expectation. So we start with the expectation calculation of the number of copies of h's in GMP. And the expected number of copies of h's in GMP is, so this means we ignore the constants. And if we ignore the constant factors, then this expectation is more or less n to the 4 times p to the 5, because h has 4 vertices, so there are more or less n to the 4 many potential copies of h. And then because h has 5 edges, so the probability for each copy of h to exist is p to the 5. So this is the expectation, and we know that if p is much smaller than n to the negative 4/5, then this expectation tends to 0. On the other hand, if p is much larger than n to the negative 4/5, then this expectation tends to the infinity. So in this sense, we can say that the threshold for the expectation is in the order of n to the negative 4/5. And this calculation gives us a trivial lower bound. Oops, sorry. And this expectation calculation gives us a trivial lower bound on the location of the threshold, because we know that if the expectation tends to 0, then typically there's no copy of h in GMP with high probability. So that means from the definition of the threshold, so here we have n to the negative 4/5. And from the definition of the threshold, we know that if p is much smaller than this n to the negative 4/5, then typically there's no copy of h. So from the definition of the threshold, we know that the threshold must be at least as large as this n to the negative 4/5. And it turned out, we know that the truth is the threshold is in the same order of n to the negative 4/5. So in this case, this expectation calculation gives us the right answer for the location of the threshold. Okay, so the lesson from the first example is, okay, so we are curious about the location of the threshold and the expectation. And in some cases, the expectation calculation gives us the right answer for the threshold. That was the lesson from this example. And now we examine another example. So here, again, our XP is GMP, and our increasing property is to contain a copy of K, where K looks like this. And again, our question is, what's the threshold for GMP to contain a copy of K? So we start from the expectation calculation again. And in this time, the expectation is about n to the 5 times p to the 6, because K has 5 vertices and it has 6 edges. So from this calculation, the threshold for the expectation, I use these quotation marks because I haven't defined it yet. I will give you the rigorous definition later. But for now, the threshold for the expectation in this case is about n to the negative 5/6. So again, this n to the negative 5/6 gives us a trivial lower bound on the location of the threshold. And from the first example, so now we ask this natural question. Then in this case, again, is the threshold equal to this trivial lower bound? But in this case, so if you have some maturity, we know that this is not the answer in this case. We know that the truth is the threshold is something much larger, n to the negative 4/5. So in this case, we have n to the negative 5/6. This is a trivial lower bound, but the truth is something larger, n to the negative 4/5. And we know where this comes from. We've seen this before. So this is the expectation calculation from the first example. And in this case, so we know that if P is much smaller than n to the negative 5/6, then there's no K typically. So this gives a lower bound on the threshold. So this gives a first lower bound on the threshold. But if P is much smaller than n to the negative 4/5, in this case, from the first example, there's no H typical with high probability. And because H is a subgraph of K, so if there's no H, then there's no K as well. So in this case, by considering a denser subgraph of K, we got a better lower bound on the threshold. And this is in general true. So Erdős and Renyi and Bolobash showed that, roughly speaking, for any fixed graph K, the threshold for GMP to contain a copy of K is in the same order, is equal up to a constant factor that the threshold for the expectation of the densest subgraph of K. So in this case, the densest subgraph of K is this H. So the expectation, the threshold for the expectation for H gives us the right threshold for the containment of K. So the lesson from this example is, okay, so in this case, first of all, in this case, again, the expectation calculation gives us the right threshold. But on the other hand, to get that, we have to look at the right subgraph of the given subgraph. So we have to look at the right part whose expectation we want to compute. Okay, so okay. So in the second example, we saw this fixed subgraph containment. And in the third example, let's take a look at a spanning subgraph. So in this example, our increasing property is to contain a perfect matching, where a perfect matching means a perfect matching looks like this. So this is a disjoint union of edges that cover all of the vertices. So this graph is not a fixed graph, but it grows as n grows. And the question is, what's the threshold for GMP to contain a perfect matching? And in this case, again, we can start with this expectation calculation. So expected number of perfect matchings in GMP is about this. I mean, so let me skip this computation, but we know that from this computation, we know that the threshold for the expectation is in the order of 1/n. So again, this 1/n gives us a trivial lower bound. And the question is the threshold equal to 1/n up to a constant factor? But in this case, the truth is the threshold is something much larger. This is log n/n. So there is this log n gap between the trivial lower bound from the expectation calculation and the truth. And in the first two examples, in the last example, in the previous example, we saw that if we consider the right subgraph of the given graph, then the expectation calculation gives us the right threshold. But in this case, whatever subgraph of the given perfect matching we consider, the expectation calculation always gives us 1/n. So in this case, really, there's this non-trivial gap between the expectation between the threshold for the expectation and the actual threshold. But it turned out this log n/n is another trivial lower bound. And this is because of the fact that if P is much smaller than log n/n, then GMP has an isolated vertex with high probability. So this is so-called the coupon collector behavior. So the question is, so the question is if there are, if there are n coupons out there, and each time we buy a cereal, each time we buy a cereal, if it contains a random coupon, then to collect all of the n coupons, how many cereal do we need to buy? So this is the question, and the answer is we need to buy n times log n cereal to collect all of the n coupons with high probability. So, and if we apply that, if we apply that theme to this, our random graph situation, then it tells us if our probability P is much smaller than log n/n, then typically there is uncollected coupons, which means in this case, isolated vertex. So this coupon collector behavior of the random graph pushes up the trivial lower bound by log n. Okay, so do we have any questions so far? Okay. So here, let's consider one last example. So so now our X is n choose R, which means we have n vertices, and then we consider all of the R tuples like this. So that means XP means we choose each R tuple with probability P independently, and this is called a random R uniform hypergraph, HRNP. And so in 1980s, Shamir asked this question: when R is larger than 2, what's the threshold for the random R uniform hypergraph, HRNP, to contain a perfect matching? Where a perfect matching in this case means we have a disjoint union of R tuples that cover all of the vertices. So of course, for this question, we need this silly assumption that R divides n, but let's not worry about this for now. So yeah, so the question is, again, if R is larger than 2, then what's the threshold for HRNP to contain a perfect matching? And when R equals 2, so this is when R equals 2, this is the example that we considered in the previous slide. And this was answered already by Erdos and Renyi in 1966. And somehow when R is larger than 2, then this problem gets much, much harder. And this is because when R is larger than 2, then we don't have an analog of Hall's marriage theorem or Tut's theorem. Anyway, so this problem was open for about 30 years, but still there are some ways to get lower bounds. So for example, so for simplicity, let's just assume that R equals 3. And in this case, if we apply our first lower bound, the expectation calculation, in this case, the threshold for the expectation is n to the negative 2. So our first lower bound on the threshold is n to the negative 2. But also we know that there is another way to get a lower bound. So the lower bound from the coupon collector, which means the probability that, the probability that there is no isolated vertex, If we compute that probability, then we have the second lower bound, which is log n over n squared. So again, we see this log n gap between the first lower bound and the second lower bound. And it was proved by Johansen, Kahn, and Wu in 2008 that the actual threshold is equal to the second lower bound, log n over n squared. So here we see this log n gap again between the first lower bound and the actual threshold. So far we have examined 4 examples, and let me summarize our observations so far. So as I said, the fundamental question is this: what drives the threshold? And so we have seen 4 examples, and from there we saw that we have some trivial lower bounds on the threshold, on the location of the threshold. From the first 2 examples, we saw that the threshold for the expectation gives us a lower bound. It gives us the first lower bound. And from the last 2 examples, we saw that the coupon collector-ish behavior of the random graph pushes up the first lower bound by log n. So these are some easy ways to get lower bounds. And historically, in many, many interesting cases, the main task is to find a matching upper bound. And then the Concolite conjecture is about getting an upper bound. So roughly speaking, it says that for any increasing property, the threshold is at most log x times the expectation threshold. So it says that, I mean, our observation says that this is the expectation threshold. And so this gives the first lower bound on the threshold. And then if we see the coupon collector-ish behavior of the random graph, then it pushes up this lower bound by log n. So this is the expectation threshold times log of the size of the universe. So this is the second lower bound. And the Concolite conjecture says that actually the threshold for any increasing property, the threshold is at most this second lower bound. So this in particular says that if we see this coupon collector-ish behavior for the given increasing property, then the second lower bound is exactly equal to the threshold of the given increasing property. So let me emphasize that this is a very strong conjecture because it immediately implies some historically very hard results. For example, the last example that we saw is this, the threshold for perfect hypergraph matchings. And this was a very hard result, and they received the Fulkerson Prize because of this work. But if the Concolite conjecture is true, then this is just a simple corollary of the Concolite conjecture. Because in this example, we know, I mean, we can very easily compute that the threshold, the expectation threshold is in the order of n to the negative r minus 1. So that means if we apply the Concolite conjecture, if the Concolite conjecture is true, then the threshold is at most log n times n to the negative r minus 1. But we also know that this is equal to the second lower bound. So this upper bound just nails down the location of the threshold. And there is another example. So this is, again, so let me not talk about the details, but this is another very hard result which is recently proved. But again, if the Concolite conjecture is true, then this is just one line corollary of the Concolite conjecture. And not just these examples, but in general, finding the location of the threshold for the given increasing property is a very hard task. But if the Concolite conjecture is true, then it just traps the location of the threshold between the expectation threshold and the expectation threshold times log term. So for any given increasing property, the Concolite conjecture traps the location of the threshold in this narrow window. Okay, so this is a rough description of the Concolite conjecture, and I wonder if there are any questions.
I mean, you said rough, so okay, but I mean, you just gave an example where the obvious expectation threshold was wrong. So
yes.
Say something more about the rough statement. There's got to be something more to it from the example you gave.
Yes, so it's coming. So in the next slide, I'll give you the rigorous definition of the expectation threshold and then the rigorous statement of the Concolite conjecture.
Okay.
Okay, yeah. Thank you for your question. And are there any other questions about what I said? Okay.
So this rough statement is wrong?
Oh, no, this is not wrong. So this is a rough statement, but the problem is, so I haven't defined the expectation threshold. So in the previous examples, I showed, in the first example, I showed this is the expectation threshold. And in the second example, I showed, so this looks like the expectation threshold, but actually there is a better notion of the expectation threshold. So I haven't given you the rigorous definition of the expectation threshold, and that's what's coming in the next slide.
Thank you. Thank you.
Okay, are there any other questions? So, okay, so yeah, let me move on to the next slide. So now let me give you the rigorous definition of the expectation threshold. So the problem, not the problem, but the difficulty is this. So our increasing, so in the previous examples, the given increasing properties are pretty concrete. So we know what it looks like, and we know who's there. So we have some good feelings about whose expectation we want to compute. But for abstract f, for abstract increasing property, it's unclear whose expectation we want to compute. So we need a careful definition for the threshold for the expectation. And to give the definition of the expectation threshold, let's start with this observation. So in the previous examples, the expectation threshold always gives a lower bound on the threshold. And this observation is again about a lower bound on the threshold. Okay, so this observation says Q is a lower bound on the location of the threshold if there exists a collection G in 2 to the X that satisfies the following two properties. The first property is G covers F, and I think it's better to draw a picture. So first of all, let's say this is our G, and then let me define the offset generated by G, which uses this notation. This means we collect everything above the members of G. So this is the offset generated by G. And we say G covers F if F is entirely contained in the offset generated by G. So this is the meaning of G covers F. So this is the first requirement for a G. And the second requirement is if we add up Q to the S for all of the members of, or for all of the members S in G, then this cannot be very large. So this is the second requirement, and we'll call this Q chip in our, so I introduced this term for our proof part. So this means, yeah, our cup, so we have a cover and it should be cheap. In that case, this Q gives a lower bound on the threshold. A justification of this observation is very straightforward from the definition. So let me not talk about that part, but let me connect this observation to one of our previous examples. So this is our example 2. And in this case, our X was n choose 2, so we were considering GMP, and the given increasing property was to contain a copy of K. So in this picture, in this 2 to the n choose 2 picture, we have the empty graph at the bottom and the complete graph on the top, and F looks like this. So F is a collection of all of the graphs that contain at least one labeled copy of K. Is this picture clear? Okay, so in this case, to apply this observation, we need a cover. And there is an obvious choice for a cover, which is we just collect everything, every minimal element of this F. So if we can let this to be G, this is G1. So for this G1, obviously G1 covers F. And if we do the computation in number 2, then this, notice that this is exactly equal to the expected number of copies of K in GMP, because we have Q to the S, this is the probability for each copy of K, and then we add this up for all of the copies of K. And this we saw that this computation gives us Q at most n to the negative 5/6, and this gives us the first lower bound on the threshold. And also in the second example, we saw that there is a better choice for a cover. So in that case, if we choose our cover to be not the collection of K's, but the collection of all of the H's, where H is the densest subgraph of K. So in this case, our G2 is slightly below our F. So this is G2. But still G2 covers F. And in this case, the computation in item 2 gives us a better lower bound. So this computation gives Q at most n to the -4/5, which is larger than the first lower bound. So from this cover, we achieved this better lower bound, and then we saw that this better lower bound is equal to the threshold up to a constant factor. So this is how we connect this observation with one of our previous examples. So the lesson from this example is, or this observation is, whenever we have a cover, when we go over the computation in item 2, this gives us a lower bound. Okay, so each time we have a cover, we go over the computation, we have a lower bound, and then the definition of the expectation at the expectation threshold is this. This is the maximum Q that admits a cover. So that means we consider all of the possible covers, and each cover gives us a lower bound, and we choose the largest lower bound. So this is again a trivial lower bound on the threshold, and this is the definition for the expectation threshold. And then now the rigorous statement of the Concolite conjecture is this. So there exists a universal constant K, so K comes first, such that for every finite set X and increasing property F, the location of the threshold is at most this constant K times the expectation threshold times log of the size of the universe. Okay, so this is the statement of the Concolite conjecture, and in the next part, I'm going to introduce our results. And are there any questions?
Sorry, it's G covers F, but but A has a subset B, which is G. That says F covers G, or in some G. B is subset of A, and A for any A is F. There is its subsets from G. Yes.
Yes. So if this is F, so cover means, so G covers F means whenever we have an element in F, if we look down, then we can find one element, at least one element in G. That's the meaning of a cover. Is that your question?
Yeah, thank you.
Yes. Okay, so let me move on to our results finally. So let me first talk about the fractional version of the Concolite conjecture. This happened a couple of years ago. So there we introduced, not we, but Telegram introduced the fractional expectation threshold for the given increasing property F. So let me skip the definition, but from the definition, it's straightforward. It is straightforward to see that the fractional expectation threshold is an upper bound on the expectation threshold, but still it's a lower bound on the threshold. So this fractional expectation threshold is some parameter in between the expectation threshold and the threshold. And a couple of years ago, with Frankenstein, Kahn, and Narayanan, we showed that we showed this statement, which is basically almost equal to the Concolite conjecture, but we replaced the expectation threshold by the fractional expectation threshold. So this, and at the end we have this L of F. This is the size of a largest minimal element of F. So which means if we have F, then we examine all of the minimal elements of F, and then we take the maximum size. This is the meaning of L of F. So this is in this sense, this is stronger than the fractional version of the Concolite conjecture, because we replaced log of the size of the universe by log of L of F. So this means in particular, if we are considering the containment of a fixed graph, in that case, L of F is a constant. So if we apply this fractional version of the Concolite conjecture, then there's no gap between the fraction expectation threshold and the actual threshold. So this is weaker than the Kahn-Kalai conjecture because, as I said, the fraction expectation threshold is an upper bound on the expectation threshold. But in all of the known applications, the expectation threshold and the fraction expectation threshold have the same order. So that means everything that follows from the Kahn-Kalai conjecture also follows from the fractional version of the Kahn-Kalai conjecture. And our proof was inspired by the Erdo-Girardot sunflower, the breakthrough of always Lobet, Wu, and Zhang about the Erdo-Girardot sunflower conjecture. Anyway, so as I said, in all of the known applications, the fraction expectation threshold and the expectation threshold are equal. So that means, so it's natural to ask, okay, then is it true that for all of the increasing properties, the expectation threshold and the fraction expectation threshold have the same order? And this was conjectured by Talleyrand. So he conjectured, so for all of the increasing properties, the expectation threshold and the fraction expectation threshold are equal. And if this conjecture is true, then this implies the equivalence of the Concolite conjecture and the fractional Concolite conjecture. So before our recent work, we thought maybe this is the most likely way to prove the Concolite conjecture. So we tried to prove this conjecture and there was some progress, but okay, first of all, even simple instances of this conjecture are not easy to establish. So in Talleyrand's paper, he suggested 2 test cases, and those 2 test cases were proved now. But so even for those test cases, it was not very easy to prove them. And the full conjecture is still widely open. So we don't know how to prove that. And our new result is the proof of the Concolite conjecture. So finally, we replaced this fractional version, the fractional expectation threshold by this expectation threshold. So this is our new result. And our proof idea is inspired by the sunflower theorem and the fractional Kahn-Kalai theorem, but our implementation is very different. And hopefully I can show you a little bit in the next slide. Okay, so for the rest of the talk, I'm gonna give you some brief idea of our proof, but before jumping into that part, I wonder if there are any questions. Okay. So yeah, what we actually proved is this reformulation. So in this reformulation, this is a little bit stronger than the Kahn-Kalai conjecture. And in this reformulation, we think H, so we will use H. This is the collection of all of the minimal elements of F. And then what we proved is this. So our statement is there exists some universal constant L such that for every L-bounded H, where L-bounded means for every element in H, the size of S is at most L. So this is the meaning of L-bounded. So this corresponds to this L of F. So every minimal element of F has size at most L. So if H is L-bounded and if P is larger than the expectation threshold of the offset generated by H, then with M this quantity, the probability that XM, so this is the random subset of X whose size is M. So the probability that XM is contained in the offset generated by H is, it tends to 1 as L tends to the infinity. And let me point out that this XM is contained in H means XM contains some element in H. So basically it says if P is larger than this L times the expectation threshold times log L. In this case, this containment probability tends to 1 as L tends to the infinity. That's the statement. And I wonder if there are any questions about this reformulation. So let me say, okay, so the original Kahn-Kalai conjecture is about an upper bound on the threshold. And then what's the meaning of an upper bound on the threshold? So the threshold means here, and giving an upper bound on the threshold means if our P exceeds this, so if P exceeds this, then it's likely that our random set satisfies the given increasing property. But in the original statement of the Concolite conjecture, this containment is enough to show that this containment probability is at least 1/2. So what we show is a little bit stronger because we showed that this containment probability tends to 1 as L tends to the infinity. Okay, so this is our reformulation. And in the next slide, I'll give a very rough sketch of the proof. Okay, so this is the statement, and then this picture says, okay, so this this rectangle is our universe X, and those circles are the elements of the given hypergraph H. And we want to show that if M is as large as this L times P times something, then this containment probability tends to 1. And what we are gonna do is this. So we choose our final random set W. So W is just another name of XM, little by little. So step by step. So in the first round, we sprinkle some of the random elements. This is the first round. And the second round, we sprinkle some more random elements. And in the third round, we repeat again and again. And at the end, if we look at our final random set, we want to show that our final random set W contains at least one element of H. This is what we want to show with high probability. I mean, yeah, so this is what we want to show. We want to show that W contains at least one member of H with high probability. Okay, and so for this random set, we are going to sprinkle the random elements step by step. And for this, we're gonna run some algorithm. And something interesting about our algorithm is we don't assume anything for this algorithm. So when we look at the statement, our assumption is this: P is larger than the expectation threshold. But in our algorithm, we do not assume this one. We just run our algorithm. And at the end, we'll show that our algorithm gives 2 possible outputs. And the first output is our random set W is contained in the offset generated by H, and there's some second output. And finally, at this point, we apply our assumption. And once we apply our assumption, then we can show that this is very unlikely, the second option. And this gives us the desired conclusion. So we can show that this containment probability is tending to 1. Okay, so in the next slide, I'll give you a little bit more details about this proof idea, but still very sketchy. And for that, let me remind you that what's the meaning of our assumption. So P is large. What's the meaning of P larger than the expectation threshold? This means, so the definition of the expectation threshold was this is the maximum that admits, the maximum P that admits a chip cover. So that means P larger than the expectation threshold means H does not admit a P chip cover anymore because T is too large. That's the meaning of our assumption. Okay, so if we apply our assumption, then we know that the offset generated by H does not admit a chip cover. Okay, so this is a little bit more details about our proof, but still very sketchy. So our goal is to show this containment statement. And as I said, we are going to choose our random set step by step. And as we choose our random set step by step, our hypergraph also evolves from H0 to H1 to H2, etc. And at each step, what happens is this. So at each step, you're going to choose a random set Wi of size L times P times X. So this is smaller than our final random set. So there is this log L gap. So we choose this Wi at random. And upon the choice of Wi, we're going to construct a cover Ui of some hyper edges in the current hypergraph. So in the picture, it looks like this. So the picture on the left-hand side is our current hypergraph. On the picture on the right-hand side shows that, okay, so these pink dots, those are the covers. Those cover some part of, the pink dots cover some of the current hyperedges. So, and those covered hyperedges are called GI. Okay, so each step we try to cover some of the hyperedges. And once we cover some of the hyperedges, then we exclude them and move on to the next step. And in the next step, again, we try to cover some of the hyperedges. So maybe in the next step, we're gonna add some more covers like this. And then this will be GI plus 1. And then we exclude them and then move on to the next step. So each step, what we are trying to do is to cover some of the hyperedges. And so here, I said construct, and in this boldface means I don't have time to explain how we construct this. Oh, I'm sorry for that. Anyway, so when this process terminates, again, so this is in the boldface, which means I don't have time to talk about the details. But when this process terminates, and I can tell you this terminates within log L steps. So this means if we choose WI at each step, then at the end, the size of our final random set is still at most M. Anyway, so if when this algorithm terminates, then we combine all of the covers UI. So we call that U. So this U covers some hyperedges. In that sense, I call this a partial cover. Then so I said there are two possible outputs, and those are the two possible outputs. The first output is either U covers all of the hyperedges, H, or W is contained in H. So this means W contains some, excuse me, some member of H. Those are two possible outputs. Okay, and then the main point is typically U, which is the partial cover, which is the collection of all of the covers that we constructed so far. Typically, U is P chip. So P chip is the summation U in U, P to the size of U. This is at most 1/2. And this is really the part that requires a clever idea. And this has to do with our construction. And once we have this main point, then we are done, because so typically U is chip. So in the picture, it looks like this. This rectangle is a sample space for the choice of W. And for typical W, our outcome U is chip. And it's very unlikely that U is expensive. So for most of the W's, U is chip. And once we have this, so this is our main point. And now, so far we haven't assumed anything. So it just follows from our algorithm. And now what happens if we apply our assumption? So our assumption was P is larger than the expectation threshold of the offset generated by H. And I emphasized that this means this H does not, let me say this. This means there does not exist a P chip cover of H. And do you see how this assumption gives us the desired conclusion? Because H does not admit a chip cover. So that means if one happens, if U covers H, then this event must be contained in this unlikely event here. So this is where one happens, right? Because H does not admit a chip cover. So if U covers H, then U must be expensive. So that means one is a subset of the event that U is expensive. So this gives us one is unlikely. So this is how the proof goes. But as I said, so really the main point is to show that, to find a way to construct a cover which is P chip. And this is where the clever idea was needed. And so let me just advertise that. So our entire proof is about 3 pages. So if you are curious about how we constructed our cover, then I think it wouldn't be so hard to read our more details, to check more details from our paper. anyway, so this is the proof idea, and I wonder if there are any questions. Is this a good silence or a bad silence?
No. Joel here, could I just make more common question? If I think of historically of the Rudel nibble, where you take a big chunk and then you take another big chunk, but after the Rudel nibble was discovered, it was found that in fact, Rudel himself found that you could also do it one point at a time. And do you think you need to choose the WIs at this size at random, or could you just be picking points or something like that?
Okay, so if I think about our proof idea, so here, this L is something large. This is a large constant. It doesn't have to be very large, but at least
Right.
we need some large constant.
Uh-huh.
And because of this necessity of this large constant, I'm not sure if we can shrink the size of each WI. So we
Okay.
need this large constant. It was essential.
Okay.
And this is what, thank you for your question. And this is one reason why we are not sure about if we can get some like a sharper result on the location of thresholds. So, so for example, if we consider just any known interesting properties, we know something much more than just, the order of the threshold. We know the exact constant, for example, but I'm not sure if we can get those better constant using our approach.
Okay, thank you.
Okay. Okay, so do I have time or should I finish now?
Yeah, you can take a few more minutes if you'd like.
Oh, okay. So yeah, because in the next part, I have some open questions. So yeah, one natural open question is this. The Kahn and Kalai conjecture gives an upper bound on the location of the threshold, and this is just an upper bound. So for many, many cases, this upper bound is tight, but still this is just an upper bound. So in general, what we know is the location of the threshold is in between the expectation threshold and the expectation threshold times some log factor. So a question now is what characterizes the gap between the expectation threshold and the actual threshold? In many, many cases, as I said, in many, many cases, this log L gap is tight. I put some examples in gray. But there are some cases for which log LF is not tight. And I think those are good test cases. And those are the questions that I'm thinking about now. And there were some successful test cases, maybe, yeah. So this is one test case. And I think this example is just too specific. So let me not go into too much details, but there is something called the square of a Hamilton cycle. And for this one, the conjecture was the threshold is equal to this quantity. So again, let me not talk about where this quantity comes from, but let me just point out that this is equal to the expectation threshold. So if this conjecture is true, then there is no gap between the expectation threshold and the threshold, while the square of the Hamilton cycle for this one, L of F is about N. So this is the case that this log L gap is not tight. And so there was some effort to prove this conjecture, and it was proved by Kahn, Narayanan, and myself that that there's actually really no gap between the two quantities. And for this proof, we modified our approach for the fractional Kahn Kalai. And so yeah, this was the first test or successful test case. And there are some other cases where there are no gaps. And one interesting example is this to contain a triangle factor. So again, because I don't have so much time, so let me not talk about a triangle factor, but it was proved by Johansson, Kahn, and Wu that the threshold is equal to this. So this is about the expectation threshold of F. And there is this log N to the 1/3. So in this case, again, L of F is about N. So the Kahn Kalai conjecture, gives an upper bound, which is N to the -2/3 times log N. So here, this gap is smaller than was predicted by the Concolite conjecture. And for this one, we don't know how to do this using our approach. So this is, I think this is a good test case to characterize the gap, the size of the gap between the expectation threshold and the actual threshold. And I think another interesting example is this K-out model. And so the motivation is this: where is this log n gap come from? We know, so in the previous example, we saw that we have this log n gap because of the coupon collector behavior. Then the natural question is, then what if we forbid this coupon collector behavior? So in this K-out model means, so this is a little bit different from the Erdos-Renyi random graph. This means we have we start with n vertices, and each vertex choose k neighbors. So in this model, there's no from the construction of this model, there's no isolated vertex at all. So in this case, do we still see the log n gap or not? And it was proved by Alan Fries that if we consider this K-out model, then if k is 2, then with probability tending to 1, GK out has a perfect matching. So in this case, indeed, there's no log gap. And our question is, okay, then can we get, so if we consider K-out model, then can we show that there's really no coupon collector behavior for all of the increasing properties? So I think this is another interesting question in this direction. Oh, and this is all that I have for today. And thank you very much for your attention.
Great, thank you very much, Jinyoung. So we have time for a question or two if anyone has questions. Actually, maybe I could ask one, which is, so the fractional expectation threshold, where do you believe it fits in? Do you believe this Talleyrand conjecture?
Could you say that again?
So you had the Talleyrand's conjecture that you mentioned about fractional expectation threshold.
You mean the equivalence of the fractional expectation threshold and the expectation threshold?
Do you believe that?
Yeah. So if I have to bet, then yeah, I try to prove that. So and then now, so that implies the equivalence of the Concolite conjecture and the fractional Concolite conjecture. So now that we know that actually the Concolite conjecture is true, so I think it also gives an additional evidence that the Talleyrand's conjecture is true. So if I have to bet, then I want to believe that that conjecture is true.
Okay, thank you. Would anyone else like to ask a question?
I have a question. So I mean, it would make sense that this that the expectation threshold would be easier to compute, but also you still have to like maximize overall covers. So it does seem like, at least a priori, it could still be sort of hard to compute. So I guess I'm sort of wondering like how you overcome that, and also like if there are any cases where, on the other hand, like it is legitimately just like hard to compute for some properties.
Yeah, I think that's a very good question. And yeah, okay, so it's true that in general, the expectation threshold is hard to compute. But if we consider this subgraph containment, which is historically very interesting questions in the random graph theory, and also historically very hard. For those questions, there is an easy way. This is just one-line computation to get the expectation threshold. And so there is a conjecture. So when we say the Concolite conjecture, when you go and look at the paper itself, then there are two conjectures. The first, and what we proved is the first conjecture, and the second conjecture says actually there is an easier way to compute the expectation threshold. So it says that, especially for the subgraph containment, we don't have to consider all of the possible covers, but the covers that consist of all of the same copies of the subgraph. But that, am I making sense? So we don't have to consider any arbitrary cover, but a cover that consists of the same copies of, so the same isomorphic copies of the graphs. But that is also open. Even that one is still open. So yeah, in general, what I can say is it's hard. Yeah.
That second conjecture is in your paper. It's listed in your paper. Or...
Oh no, so that is in the original Kahn and Kalai paper, the paper by Kahn and Kalai, and that conjecture is still open.
Okay, cool.
Yeah.
All right, thanks.
Oliver has a question.
It was basically the same question, but maybe then it asked the second part of it. So is it known that if the original property has some symmetry, then you only need to consider covers G that have the same symmetry, for example, or something? Does that make sense?
Yeah, so that's a little bit more general than the answer that I had. Is that right? So if we, so the subgraph containment is very symmetric, and then even for that one, it's unknown. It's unknown that if we can, if it's enough to consider.
It's not quite the same, because with subgraph containment, if you know it's symmetric, that still doesn't tell you it's counting copies of one subgraph, because it could in principle be that there are sort of two to consider or something. So I think it's not strong, neither stronger nor weaker.
Oh, yeah, I don't know. Yeah, I don't.
In the various examples, you said, this is the expectation threshold. So is that a sort of ad hoc argument in each case, or is there some tool that helps? You said, for example, for the matchings, the expectation threshold is this, or for the square of the Hamilton cycle, it's that. How are those ones calculated?
Oh, so what happens is, okay, so it's a computation. I don't know if I want to go over this computation. Yeah, but okay, so in general, so for the subgraph containment is one-line computation, and in general what we know is, so the fraction expectation threshold is, it gives an okay, so first of all, it's very easy to get a lower bound on the expectation threshold, because whenever we have a cover, it gives a lower bound. And so, for example, if we consider the perfect matching, then we know that 1/n is a lower bound. And the expectation threshold is at most the fraction expectation threshold. And by the linear programming duality, the fraction expectation threshold is at most something called spread. I don't know, so something called spread. So this comes from the LP duality, and the spread is easy to compute. And for those subgraph containment, we can easily show that, for example, for the perfect matching, spread is at most 1/n up to constant factor. So that nails down the expectation threshold.
I see.
I would jump in. You just answered my questions that have been inadvertently, but I was sort of wondering exactly how cheapness and spread relate to each other. Is it just what you said, or is there sort of more sophisticated things happening there?
Oh yeah, so the cheapness and the spread, that's exactly what happens between the expectation threshold and the fraction expectation threshold. As I said,
okay.
The fraction
So you totally got it. Okay, I was just waiting to jump in. Thank you.
Okay, maybe this is a good point to stop the recording and then invite everyone to unmute and give a big round of applause.